All right. So we left off with just one proof left to do. Remember, we were talking about proof by contrapositive. And so the last one we have to look at is when there are multiple hypotheses in a conditional statement and how we can do a proof by contrapositive with that. Okay. So we'll just look at a case where we have two hypotheses and we have this implication. Hypothesis 1 and hypothesis 2 implies whatever our conclusion is. And we want to show that these two things, okay, are logically equivalent. We'll go ahead and do a truth table. This is a good chance to practice this. So we do have 3 variables. We will need 8 lines, but there's a lot of repetition. So let's look at H1 and H2 implies C, and then we'll compare it to this one right here. Okay. So let's do, for our H1, we'll do alternating 4 trues, 4 falses. Okay, and then this will alternate 2s, oops, 2s. I didn't draw these very well. I'm going to have to put lines. Okay. True, true, false. Okay, there it is. False. True, that should have been true. False, false. Okay, and then this one can alternate ones. True, false. Okay. All right, so over here on this one, H1 is the same thing. That was alternating 4s. Okay, this is not C. All right, so this was alternating 1s, true, false, so we'll just go the other direction, false, true. And H2, this is not H2, we were alternating 2s, so we'll just do the opposite and do false, false, true, true. Okay, so the only time a conjunction is true is when both of the operands are true. So we see that here, we see that here, and none of the rest have double trues. So the rest of them are falses. Okay, and then the only time we have a false implication is with a true hypothesis. So notice the hypothesis is under the and here. Okay. So let's look. All of these falses, false hypothesis, it's always true. So those ones are all true. Okay. The only ones we really have to consider are the ones at the top. So true implies true is true. True implies false is false. All right, same thing over here with a conjunction. We just look for both trues there. There should be one other spot there. Everything else should be false. Okay. And then for our implication, anytime we have a false hypothesis, we know the implication is true. So all of those falses are going to give us trues. Okay, so true implies true is true. True implies false is the only place we'll get false. Okay, so if you look at this one right here and this one right here, they are exactly the same. Okay, they are logically equivalent. All right, so why do we go do all of that? Was it just because we haven't done truth tables in a while? No, it is not. Okay, so let's see what this means. Okay, so if I have 2 hypotheses, okay, in the conclusion, notice to do a proof by contrapositive, I can move one of the hypotheses over to the other side of the implication and negate it, okay? And then I can put the negation of the conclusion along with one of the hypotheses as it was. Okay, so I can leave that one there. I don't have to move both of them over. Okay, normally we would think of the contrapositive of this as not C implies, and then you would move everything over, and you would put not H1 or not H2 on the other side, right? Okay, but you can leave this one over here, okay, and it's still equivalent to the contrapositive, okay, or to the original statement, which is also equivalent to the contrapositive. So all of those things are equivalent. So it's enough for you to just negate the contrapositive, negate one of the hypotheses, and you can leave, and if I had like 3 hypotheses in there, you could leave 2 of them, okay? You only need to negate one and put it on the other side. So that will be very helpful in some instances where you have, a tricky hypothesis that you'd like to try to get as the result. You only have to move that one. You don't have to move all of the hypotheses. Okay, so here is a good example of where we might want to apply that. Okay, so if we were to write that out, so x is an even integer. That's part of our hypothesis. And y squared is an odd integer. That's also part of our hypothesis. So this is like h1 and h2. Okay. Then y plus, or x plus y is an odd integer. That's our conclusion, right? This is our conclusion. Okay. And so, looking at, okay, x is an even integer. I love that hypothesis. Y squared is an odd integer. That one's trickier, okay? Because, like, if we know something about y, it's easy to reason about y squared. But if you just know about y squared, it's hard to reason about y, or, the square root of it. So this, as a hypothesis, this is a little bit of a tricky one, okay? And then x plus y being odd, that's wonderful. Okay, but it's this one that's really tricky. And it would be really nice if we could move that and have that as the result, as something that we're trying to prove as the conclusion. Okay, or the negation of that, right? So if we knew something about x being so if we rewrite this as h1, leave that one, okay, and negate the c, and then implies, and then move the negation of this one to the other side. So we just proved on the previous page that that would be logically equivalent to the original statement. We can leave one of the hypotheses there, okay, put the negation of the conclusion as a hypothesis, and a negation of one of the other hypothesis as the conclusion. Now, if we think about that, that's going to be much easier to deal with. So not C, that would be, so this would be x plus y is, so I've now gated it, and so instead of being odd, it's even. So x plus y is even, and our original hypothesis 1, x is even. Then negation of hypothesis 2 would be that y squared, instead of being odd, being even. Okay. And that looks much easier to do, right? So we know something about x, we know something about the sum of x and y, and now we need to reason about y squared. Okay. So, if we can prove this one, that is equivalent, that is a proof by contrapositive, and it is equivalent to proving the original statement that they asked for. So that is our goal. That's what we're going to try here. Okay. So we use a proof by contrapositive. To show that, okay, if x is even, I'll just put x being integers even, and y integer such that y squared is odd, then x plus y is odd. So we told the reader that we're using a proof by contrapositive, but now let's kind of make it really clear for them what we're going to do. Okay. That is, we assume that, okay, so this one, x plus y is even, and this one, x is even, and then show that this x or y squared is also even. So now we know where we're going. Okay. All right, and you know how it goes. X plus y is even. Okay, so by definition of even, there exist. Okay, so we know that we're going to want to do something for x plus y, and we know that we want to do something for x. And here's the trouble that some people ran into on the test, is they're like, oh, x plus y is even, so it has to be 2k plus 1. X is even, it has to be 2k plus 1. And then you just wrote 2k plus 1 for both of these things. Okay. But now, if I write 2k plus 1 for both of them, now I'm saying that they're equal. That's a problem. I have to make sure that when I let them be arbitrary numbers, I can't force them to be equal by choosing the same k for both of them. So that's what some people ran into. So we need to choose two different integers, okay? Maybe just get away from the 2k plus 1, a, b, j, k, m, n, just something. But they have to be different numbers, okay? So let's just do a and b. There exist integers a and b, okay, such that, well, I know x plus y is even, so this is 2 times some integer a. X is even, so that's 2 times some integer b. And notice, like, maybe maybe they happen to be the same number, but they certainly don't have to be, and probably they aren't. Okay. Really, they can't be, because then y would have to be 0, and then it can't be odd. So, okay. So, but that's what we know there. All right. So, that's what we know, and now we have to look at, okay, well, those are the things I know. These are the assumptions. I've used definition on the assumptions that I've made. And now I need to start thinking about y squared. So I need to get from here to y squared. Okay. And if I'm going to get to y squared, it would be really nice if I had y. So any idea how I might isolate y and get an expression for y? Yeah, Carlos. Yeah, okay, great. So let's say, substituting the second equation into the first. Gives us that 2b plus y equals 2a. And so that means y must be 2a minus 2b. Okay. So now that I know what y is, I can start thinking about y squared, right? So y squared is, well, I just got to square this. Okay, so that's going to be 4a squared minus 8ab plus 4b squared. And now what am I trying to do with y? I'm trying to show that y is even. Or sorry, y squared. Y squared. Can I show that y squared is even? Yeah, pretty easily. I just have to show that it's 2 times some integer. So let's go ahead and factor a 2 out of there. So I'll have 2a squared minus 4ab plus 2b squared. Okay. And this is the other place that a couple people... They got so excited that they got here, they're just like, bam, I'm done. And they forgot that's that, okay. We still have to show one thing. And what's the last thing that we need to argue before we're really, really done? Yeah, that this thing is actually an integer, and it's an integer because the set of integers is closed under multiplication, addition, subtraction, all of that stuff is in here. Okay. So there's a couple ways that we can go about this. Let's just, we haven't used k, so let k equal 2a squared minus 4ab plus 2b squared. Okay, since the set of integers is closed under addition, subtraction, and multiplication, k has to be an integer. Okay. Since y squared equals 2k, okay, by definition, it is even. Okay. And if we go back, remember we explained what we were going to show. We were going to show that y squared is even. I've done that. And so I have accomplished what I set out to do, and I am done. So this is really handy when you have multiple hypotheses and one of them is difficult to work with, okay? But if you put it as a conclusion, it would not be so difficult. So you can use a proof by contrapositive in that case. Okay. If you're wondering, do I think you'll ever see this on a test? The answer is yes. Yes, you will. Okay, so, put a big star on that page. Make sure you know how to do those. Okay, so that is all we have about proof by contrapositive. So far we have seen a direct proof, which you guys have already done. And we have seen proof by contrapositive, which is really just a direct proof of the contrapositive. So it doesn't really feel that different from a direct proof. Yes?
Sorry, I just have a quick question. Are
yes.
you recording this lecture?
Yes, I am. And I will post it. Okay. So we still want to look today at proof by cases. Okay, proof by cases. You can do proof by cases as sort of a subcategory of a direct proof or a proof by contrapositive. So we'll maybe see a couple of those. And then we will also hopefully get through proof by contradiction. At least we might not finish it, but at least we'll get through enough that you will be able to finish up all of Chapter 3 homework before our next class on Tuesday, even if we have a couple leftover proofs that we need to warm up with next time. Okay. But, so notice that their Zybooks 3.5 through 3.7 is due next Tuesday before class, so happy weekend. Okay, so the next thing we want to look at is proof by cases. All right, so in a proof by cases, sometimes it's difficult to just say, pick an arbitrary element out of the domain, because there might be different characteristics, and you can't get one that's quite arbitrary. You'll see what I mean when we get to some examples. Okay, but it might be easier if you partition or separate the domain into different categories, into different subsets. Okay, where each of those different partitions has some characteristics, and you can choose an arbitrary value out of that one. For example, one of the classic ones is you might partition the set of integers into even integers and odd integers. And all the even ones act alike, and you can pick an arbitrary even integer, and all the odd integers act alike. You can pick an arbitrary odd integer, and it's maybe easy to make an argument if you know it's even, easy to make an argument if you know it's odd, but it's really hard to just make an argument if you have an arbitrary integer and you have no idea whether it's even or odd. Okay, so so there are other cases as well. We'll do a few different examples, but you can imagine probably when you might want to partition your domain into various classes or cases, and then you can just go through and do a separate proof for each one of those classes or each one of those partitions, each one of those cases. So every partition is going to be a particular case. Okay. So let's look at some examples of that. All right, so if integers x and y have the same parity, then x plus y is even. Okay. So if we just say, let x and y be arbitrary integers, well, then I can't guarantee that they have the same parity, right? So same parity means that x and y are both even, or x and y are both odd. And so you can pretty easily see what our cases are. Okay, we're going to have one situation, one case where we partition the all possibilities, like, you know, if I listed out all the pairs x and y that could come up, you know, half of those are going to be in the class where x and y are both even, and the other ones are going to be in a class where x and y are both odd. And we have to kind of do separate proofs because the numbers have different forms when they're even and when they're odd. Okay, so there are two cases when x and y are both even and when x and y are both odd. Okay. All right, so there are two cases to consider. X and y are both even, and x and y are both odd. So I like to kind of just label mine. Case 1, so you can kind of tell. Now you can basically write a direct proof for this first case. So we're going to write a direct proof for the first case where x and y are both even. So assume integers x and y are both even was our first case. I'll just make it one sentence and we show x plus y is even. All right. So by definition of even, there exist integers a and b such that, you know, x is even, so it could be 2 times a, y is even, so it can be 2 times b. Just don't choose the same variable. We can't force them to be equal. We just need them to both be even. Okay. All right. So then x plus y would be 2a plus 2b. And you know how this goes. We can easily see that we can factor out a 2. And all we need to do is show that x plus y is 2 times some integer. It's very important. We have to really, to meet the definition, we have to show that that's an integer. Okay. Since the set of integers is closed under addition, a plus b is an integer, and so x plus y is even by definition. Trying to be concise so I don't run out of room. All right, so we considered the first case where they were both even. We showed then that the sum had to be even. All right, then for our second case, we would assume x and y are both odd. And again, we would have to show that the sum is even. So it's going to look very much like the previous one, right? Except instead of being by definition of even, we're going to have to do definition of odd because this time they're both odd. So by definition of odd, there exist integers, okay, I'll call them m and n, just so we don't confuse them with the previous a and b. This time, since x is odd, x is going to be 2a plus 1. Since y I also assume to be odd, y is going to be 2b plus 1. Oh, thank you. And then I need you guys to keep me honest. Okay. So then x plus y will be 2m plus 1 plus 2n plus 1, which is 2m plus 2n plus 2. And if I just factor out the 2, I get 2 times m plus n plus 1. All right. So, of course, our only job is to show that x plus y is 2 times an integer to get it to meet the definition. So I just have to make sure that I show that m plus n plus 1 is actually an integer, which is easy to do. So since z is closed under m plus n plus 1 is definitely an integer, and therefore x plus y is even. So really, this looks, sometimes you just can't, like, couldn't make a general argument about parity, because parity means odd and even. You're not just going to be able to make a general argument without specifying what the parity is. So the best way to do that is just to break it into cases. Okay. And yes, it kind of makes you write twice as many proofs, but it's still all just one proof. But you have to cover the entire domain. Okay. The domain is infinite, and just the fact that I only had to do 2 cases still means that you saved time. It was a lot shorter than an infinite number of cases. I see some people still writing. I'll leave that there if I can. Okay. The next one we want to look at is for all real numbers. We haven't done a lot of real numbers, so this will be a good fun one to do. X and y, the absolute value of x minus y equals the absolute value of y minus x. Okay. And you can't just say, yeah, I've done this so many times, I know it's true. I don't care how many times you've done it. Okay. Remember, you can't prove by example. We need to make a general argument. Okay. So, the trick with subtracting numbers, if x is bigger than y, then I get a positive number. If x is smaller than y, I get a negative number. And so that's what makes the argument tricky, is you have to kind of know what the relationship between x and y are. Okay, so the way that we can partition the domain, and this time, is to think about the relationships between numbers. Okay, x could be greater than y, x could be less than y, x could be equal to y. Okay, like those are the only possibilities. So if we consider all of those cases, we've covered every possible option. Okay, and there's nothing else to consider. But it's hard to make a general argument about this if you don't know the relationship between x and y. So we have those 3 cases to consider. Okay. So let x and y be real numbers. We will use a proof by cases to show that the absolute value of x minus y equals the absolute value of y minus x. Alright, case 1. Assume that x is greater than y. Alright. So if we have that x is greater than y, the absolute value of x minus y is equal to, okay. Well, if x is greater than y, we know that when we subtract and do x minus y, we're going to get a positive number. When you take the absolute value of a positive number, you just like take the absolute value bars away and you're done, right? So the absolute value of x minus y is just going to be x minus y. Let's think about the absolute value of y minus x. Okay. Well, if x is greater than y, I'm taking a small number and I'm subtracting a larger number. When I do that, I'm going to get a negative value. So if you have a negative value, how do you find the absolute value of a negative value? You have to multiply it by -1. Right, so I'm going to have negative and whatever I got, whatever my difference was. Okay. Oh, yes. I think everybody's done with this one now. All right, and if I distribute that negative through, I get negative y plus x. And of course, if I use the commutative property of addition, I can rewrite that as x minus y. Okay. Therefore, we see that, this is equal to x minus y. This is also equal to x minus y. So I can just say, therefore, the absolute value of x minus y equals the absolute value of y minus x. That's what I was trying to prove. So I'm done with that case. Now I have to go on to the next case. Okay. So assume the other way happened. Let's say x was less than y instead. Okay. Very similar in nature, but this time, what's the absolute value of x minus y going to be? Yeah, so let's do all the, it's going to have to be negative. I'm going to have a negative product, or a negative difference, so I'm going to have to negate that. Okay. And like you said, it's going to end up being y minus x. Okay. And the absolute value of y minus x, this time y is the bigger one, so when I take y and I subtract x, I'll have a positive number, and then I can just take the brackets away, and I just get y minus x again. So once again, we have that these two are equal. And our third case is when x and y are actually the same thing. So what is the absolute value of x minus y if x and y are equal? 0. And same thing if it's y minus x. So regardless of their relationship, whether x is less than y, x is greater than y, x is equal to y, in each case, those two absolute values will be the same. All right. Next example. And you're going to feel a little bit like this one is painful, but there's a reason for the pain so that we can motivate it to not talk about another concept. So you'd have to bear with me. All right. So for integers x and y, if the product xy is odd, then x is odd and y is odd. Okay. So let's write this out. Like if xy is odd, then x is odd and y is odd. So once again, we have this situation where, like, if I know individually about the parity of x and y, it's pretty easy for me to then reason about the parity of the product. But if all I know is the parity of the product, and I don't know anything individually about x and y, it's really hard to do. So probably what we want to do is a proof by contrapositive, where I can make these things over here, individually, those can be my hypotheses, and then the product can be my conclusion. Okay, so much easier to do if I know individual parities to then argue about a product or some kind of mathematical operation on them. Okay, so proof by contrapositive is probably the way that we want to go with this. So I would turn this into not x odd and y odd. Therefore, not x, y odd. Okay. So we know from De Morgan's law that if I negate this, this is going to turn into x is even or y is even. Then the product xy is even. And this is why we need a proof by cases. If I have an and here, I can just say assume that x is even and that y is even, and I can go from there. Here, it's either this is true, or this is true, or they're both true. Like those are they really, and essentially there's three different cases, but I could have, you know, so there's, yeah, unfortunately there's three cases. There's three ways for this to be true. Let's say if they're both true, if one of them's true and one of them's false, or if the first one's false and the second one's true. Okay. So let me write those out. So we're doing a little bit of work on the side. So we could have x is even. So this one is true. Y is even. We could have this one true and this one false. So we could have x even and y odd. Or we could have this one false and this one true. So if you'll notice, if I were to say something like, assume that x is even, okay, then that would be enough for me to cover both of these cases. Okay. And it doesn't matter about what y is. So that could be one case where x is even and I make no assumption about y whatsoever. And then my other case could be that x is odd and y is even. Because I can't have y be anything in that case. It would have to be even. So that will save us from having to do three cases at least. Okay. But you can see, like, those are initially I put it into three partitions, and then I was like, hey, if I just ignore this one, I can make it over into two partitions, and that's easier. Okay, so we use a proof by contrapositive. Okay, so that is, okay, we show that if x is even or y is even, then xy is even. All right, so here's case one. So case one, we assume x is even. So then there exists an integer, we'll just call it a, such that x equals 2 times a. And so we wanted to argue that the product xy is even, so let's just multiply both sides by y so that we have an expression for the product. Okay. And so if I just kind of carefully place my parentheses there, in order to show that that is even, which is what I want to do, I just simply need to make an argument that y is an integer. Well, since the integers are closed under multiplication, has to be an integer. Notice we had, I guess I never specifically said, I forgot to write that x is an integer, y is an integer, but yeah. X is an integer here, y is an integer here. Okay. So since set of integers is closer to the multiplication, that has to be integer. Okay, therefore, by definition, x, y is even. And then case 2, and this one we assume that y is even and x is odd. Then there exist, let's do m and n integers such that, let's see, y is even, so y has to be 2 times m. X is odd, so x would have to be 2n plus 1. All right, so when we when we multiply x times y, we're going to get 2m times 2n plus 1. And we can rewrite that as, I'm just going to leave that 2 out. I'm only going to distribute the m through, so I can leave that 2 out. And that will be 2mn plus m. Okay, and then since set of integers is closed under, so we have multiplication here, addition here, we have to list both of those. Multiplication and addition. We know that 2mn plus m has to be an integer, and therefore that product is even. All right, so once again, we had to write 2 different proofs, but really that was the only way to cover the or here. It's nice when you have an and with your hypotheses, because there's only one way for that to be true. Both of them are true. But there's 3 different ways to get a true value for an or, and so there's a lot more to cover there. Fortunately, like if you group them together wisely, you can work it out. All right. So sometimes the proofs for different cases are so similar that it gets to be repetitive, and you really don't need to include both cases. Okay, so often you can just merge the cases into just one general case by using the words without loss of generality. It's such a good mathematical term. And often mathematicians will abbreviate that WLOG, just like such that is like ST, because they don't want to write the whole thing out. They just say, everybody knows WLOG means without loss of generality. So we will, in the spirit of wanting to be brief, we will do that as well. Okay. So let's look at an example here where we have for 2 integers, x and y, if 3 divides x or 3 divides y. So again, we see this or come up. Okay. So we don't want to have to go through all the cases, every single one of them. Really, it would be okay for us to say, like, as long as one of these is true. We could, I don't know which is x, which is y. I'm just going to say, in general, if 3 divides one of them, okay? I don't care about the other one. As long as it divides one of them, the proofs are going to be exactly the same. They're so similar that I don't need to cover, oh, let's say this one is true and this one is false, or this one is false and this one is true. The proofs are exactly the same. So it doesn't make sense to go through and just change all the x's to y's and repeat it. Okay. So let's look at how we can make this a little bit shorter. Okay. So let x and y be arbitrary integers. And then we'll do our without loss of generality. Assume that 3 divides x. We show that 3 also divides x times y. So if this is true, okay, guaranteed this whole thing is true. And so I would have that implies that you get with it, okay? So the other way that I could do it is if, I could also do 3 divides y, but it's going to be exactly the same proof. I'm just going to change all the x's to y's. So rather than having to write the same thing twice, with x's in one direct proof and y's in another direct proof, I'm just going to say without loss of generality, I'm just going to show you what the case when this one is true. And I'll let you, as the reader, realize that the proof is going to be the exact same if 3 divided by y was true. I would just replace all the y's with all the x's in this proof of y's. So it's not worth all of our time to rewrite it twice. So we just say without loss of generality, we'll just pick that one is true. All right, so since 3 divides x, there is an integer a such that, what's the definition for divides? Yeah, good. So in this case, x equals 3 times a. Okay. So I don't have a k, I have an a. So that means that I can take 3, multiply it by some integer value, and get x. Okay, so when I take x and I try to divide it by 3, I will get an integer answer. Okay, so I know that that's true. Okay, and I need to make an argument about xy. So once I can just multiply both sides of this by y. Okay, so xy has to be 3a, times y. And again, just kind of putting some carefully, wisely placed parentheses there helps me see, okay, does 3 divide xy? Well, if it did, then I would have to be able to write xy as 3 times an integer. So my only job is to show that ay is an integer. If it is, it meets the definition for divides. Okay. So because ay is an integer by closure under multiplication, let's see, 3 divides xy by definition. And that is what I set out to prove. And there's no need for me to do a separate case where I also have a, well, let's assume 3 divides y. I would just put a y here, I would put an x here, and I put an x. It would be the same proof, right? There's no reason for me to write it out again. Yes?
What's the difference between this one and the other one where we need that third case when they're both true?
Yeah, so, yes, that's a good question. So on this one, okay, what we could have done is we could have rewritten this even better with saying assume that x is even without, or is odd without even, sorry, because we did proof by contrapositive. Okay, assume that x is even without loss of generality. That would cover this one, okay? And then if you're thinking about y being, then you could, if you did y even, it would cover these two, okay? And it would be the same proof but replacing x and y, okay? And so I don't need to do, so this one is y is even, these two is x is even, and the proof would look exactly the same way as this one, just replacing it with x and y. So rather than making this third case, I would group these two together and say y is even, who cares about x? The other case is x is even, who cares about y? And so I can reduce that all to one general case, just x is even, be done with it. Yeah, so you can say here, oh, I wish we used without loss of generality and assumed x even. Okay. Because that would have saved us half the work. We could have completely eliminated that part and we could have just done this. Okay. So as I was saying, we went through all this pain and then we learned about without loss of generality, and then we were like really, really thankful that we learned about it, because if we knew it, it could have saved us from having to do that. Okay. So you already anticipated what I was going to talk about. Okay, good. All right. So look for those generalizations if you can, because they can save you a lot of time. Okay, and they can keep you from having to do so many cases. All right, the last proof technique that we want to look at is proof by contradiction. Okay. And so we'll first of all look at like the logic behind it, and then we'll do as many examples as we can. We probably won't get through every single one of them. We'll probably have maybe 2 left over for next time. But enough to get you started and to finish up the homework in this session. Okay, so a proof by contradiction. So let's say you're trying to prove if this hypothesis, then this conclusion. Okay. So the idea behind the proof technique is that I'm going to show that that not H implies C implies F false, that F is a false. Okay, so that this implication is true. Okay. So let's think about this. If this implication is true, how could that be true? Well, if I have a false conclusion, the only way for this implication to be true is that the hypothesis must have been false. Right? The only time that something implies false is true is when it's false implies false, not when it's true implies false. Okay. So the only way for this thing to be true is for the hypothesis to be false. So that means that the hypothesis, and at least these are the same, it has to be false. Okay. Everybody there? Okay, if I've got a truth table and I'm doing P implies Q. I still see puzzled books, so we're going to do it. And I have true implies true, I have true implies false, I have false implies true, I have false implies false. Okay. This is the only false, all the rest of them are true, right? So, if I look at an implication and I know that the conclusion is false, okay, that happens twice. That happens here and that happens here. Okay. All right, but I tell you that definitely this implication is true. Okay, so definitely the implication is true. This is the only line of the truth table that it could come from, right? So what does that mean? That means the hypothesis had to be false. That's the only way for this to happen. For the conclusion to be false and the implication to be true, the hypothesis must have been false. Okay, that has to be false. So if this is false, it means this is true. Okay. And that's what we're really trying to prove, is that this is true, but we're kind of going about it in interesting way. Okay. But believe it or not, this is a really, really common, guess like this, you know, there's just some problems that lend themselves to this kind of reasoning more naturally than a direct proof. Okay. All right, so that's the logic behind how this is working. My goal is to prove that H implies C, but the way that I'm doing that is by showing that this implication is true, that not H implies C implies false is true. Okay. Now one more layer of depth. Okay, so showing that this implication is true is logically equivalent to showing this implication. Okay, and this one is pretty easy to see. Okay, so what is the implication law? Tell me that H implies C is the same as not H or C. Okay, so I could replace that implication with that. Okay, and if I use De Morgan's law to distribute the negative, not H is H, this turns into an and then I have to put that right there, right? So these two things are logically equivalent. Okay, so really, like, I'm trying to think about this, but this is what I'm doing. Okay. So I mean, this is the way that you're gonna. These are the things that you're going to see in the actual proof. Okay. So what we're going to do is we're going to assert that H is true. That's this part. Okay. And then assume or suppose that not C is true. And show that when this is true, okay, I get some false value. False means I just find some kind of contradiction. Because the contradiction law tells me that, you know, like a lot of times where we're going to see a contradiction is where I see this thing is true, and then I prove that this thing is not true. Something can't be true and not true. That's a contradiction. Okay. So we just have to show that we get some kind of contradiction. That contradiction is a false value. Okay. So when we get that, okay, essentially we've shown this. Okay. And so, because we've shown this, we can conclude, well then our H implies C must have been true. Remember, that was our whole goal, to show that H implies C. Okay? And so we already knew that H was true, and so we can conclude that C is actually true. That H does indeed imply C. But we didn't get there directly, we did it in this roundabout way. So it's this idea. We say, well, H is true. I'm trying to show that C is true. But let's just entertain the idea. What would happen if C wasn't true? What if C was false? And you say, well, if C was false, then this bad thing would happen. It's impossible. We can't have C be false. Okay, so C really must have been true. That's, you know, here's all the logic behind it, but that's the layman's description of what's going on here. I assume H is true, and I say, well, what if the conclusion wasn't true? And I show that it leads me to this thing that can't possibly happen. So the assumption that I made here about C not being true, that was absurd. It has to be true. All right, so if 3n plus 2 is odd, then n is odd. Okay. Now, truth be told, if you had to do this proof, you would do a direct proof. But we're going to go ahead and show that you can use an indirect proof. Okay. There are other ones where it's actually more natural to use an indirect proof than a direct proof. But this one, we're going to just do it just to show that you can. Okay, because, you know, your book is going to make you do that too. Okay, so think about, all right, we have 3n plus 2 odd. Okay, that's our hypothesis. Then n is odd. And odd. That's our conclusion. Okay. It's probably a good idea to alert your readers, hey, we're going to use a proof by contradiction, just so that they're mentally ready for it. So we use a proof by contradiction. To show that if 3n plus 2 is odd, then n is odd. All right, and how do we start? Okay, so we start by asserting the hypothesis. So we say, let 3n plus 2 be an odd integer. Okay. So I'm just, this is asserting my hypothesis. And now I'm going to entertain the idea of what would happen if my conclusion wasn't actually true. Okay. So let's suppose that, so what am I trying to prove? I'm trying to prove that n is odd. So let's see what would happen if n were even. So suppose n is even. So this is where I assume or suppose the negation of the conclusion. Okay. And then I run with that and see where that would lead me. Okay. All right, so we have, but I don't know what I keep, this is going up and down, I'm having a little ride, and I don't know what I'm hitting. Oh, I think I'm leaning, there's arrow, okay, I see it, what it is. I'm sorry that I'm, seem to be on the waves here. Okay, so by definition of odd and even, okay, so we have one odd, one even. There are integers, let's call them a and b, I guess, such that, okay, so we know that 3n plus 2 is odd, so we're going to have 3n plus 2 be 2a plus 1. And we know that n is even, okay, so we're going to have n be 2b. Okay. And then by substitution, so let's see what happens if we take this value and shove it up there into that first equation and see what would happen. So we'd have 3 times 2b plus 2 would equal 2a plus 1. Let's take this to the other side. So that would give us that 2 equals, let's do 2a minus 6b plus 1. And so 2 would be in the form 2 times a minus 3b plus 1. So that statement right there, like, what are the implications of that statement? That 2 must be an odd number. Okay. So, since the integers are closed under multiplication here, subtraction here, multiplication and subtraction, a minus 3b is an integer, and therefore 2 is, well, I'll just say it, let's say it, and therefore 2 must be odd. Okay. And so when you get something like there, you're like, well, that's wrong, right? Okay. So, but this contradicts the fact that 2 is actually even, right? So there's our contradiction. We've reached the contradiction. So this is where we've taken this implication and we've shown that it implies false. That this and this implies false. So if I go back to the previous page, that's what I just did. This and this implies false. All right? So therefore, whatever here we supposed, that can't be right. So really n is not even, it's got to be odd. Therefore, n is odd. I bet we need another one of those, huh? Yeah.
I do have a question.
Yes, we do.
So does it not matter that we have a 2 left on the left side?
Nope. I mean, that's the only, like, that's the nice way to put it so I can see the contradiction. If I moved it, I mean, I suppose if I put 2 on the other side, I would have had 0 equals, and I would have had I could have had it, I would just have an extra 1 in the parentheses. It still would have worked. Okay, but some of you don't know that 0 is an even number, so you might not have seen that contradiction. So,
It's just to get the formula 2k plus 1.
yeah, it's just so we can get the formula 2k plus 1. Yeah. Okay. I mean, the other thing we could have done is we could have subtracted 1 over here, and then we could have seen, oh, well, I now have 1 is equal to 2 times an integer, and I could have shown that, oh, 1 must be an even number. Okay, so there's a different contradictions that you could come to probably. Okay, for me, the 2 was easier to see than the 0 because, yeah, some of us. Maybe I should have forced us all to, come to grips with that. All right. One more, this is probably all we have time for. So, we need to prove that the sum of an irrational number and a rational number is irrational. Okay. Now, this is an example where a proof by contradiction is a really good idea because doing a proof by trying to do a direct proof is really, really difficult. Okay. So we have a definition for rational. So rational, our definition for rational is there exist 2 integers that I can put them in, so if I say that x is rational, and there have to be 2 integers and their ratio is equal to, x. If I want to prove that x is irrational, I have to prove that there's no way to find 2 different integers, x and y, such that their ratio is x. That's way harder to do. That's really hard to do, that you prove that you can't find any integers. So, well, what about this one and this one? Okay, you'd have to consider an infinite number. It's really, really hard to prove that something's irrational. It's much, much easier to prove that something is rational. You just show that you can write it as a ratio of integers. But to show that you can't write it as a ratio of integers is very, very difficult. So trying to do a direct proof, impractical. Okay, so thinking about that, let's rewrite this. The sum of an irrational number. Okay, so let's say x is rational. Irrational. Okay, that one's ir. And a rational number. So I have x is rational, and let's say y is rational. So I've got these 2 numbers. Then I want to say that their sum, so x plus y, is going to be irrational. Okay, so that's really what we're trying to do. But sometimes it's easier to write, okay, so that you can see these are my hypotheses, these are my conclusions. Okay. Proving that something is irrational, super hard. Okay, so we're not going to go about it directly. We're going to go this roundabout way. Okay. So we use a proof by contradiction. Okay. To show that stuff. Okay. I'm not going to write it all out in the interest of time. Okay, so I saw some people already packing up like you're going to leave me. Okay, all right. So we start by assuming our hypothesis. So let x be an irrational number and y be a rational number. Okay. So that is asserting our hypothesis. And now we're going to entertain the idea that the conclusion is false. Okay. In other words, that x plus y is really a rational number. So let's suppose what would happen if that were true. So suppose that x plus y is actually rational instead of irrational. Well, now we can start saying things about, here we have this rational thing and we have this rational thing, that we can try to, we know what the definition is, that we can work with that, with those. So by definition of rational, let's see, there exists, let's do A, B, C, D. They're integers, let's see, let's make B and D the denominator. So B can't be 0, D can't be 0. Okay. Such that, okay, Y is a rational number, so we'll write Y as A over B. And X plus Y is a rational number, so we'll write that one as C over D. And then, you guessed it, we'll substitute the first one into the second one. So by substitution, okay, X plus this A over B equals C over D. And now let's isolate X. So X is going to be C over D minus A over B. Okay. And so if we get a common denominator of BD, that will turn into BC minus AD. Okay. So here's what we have. X is equal to BC minus AD over BD. So if we have that, and it's true, what can we conclude from that? Yeah, as long as these are integers, then we'll get that X is rational. Okay. Are these integers? Sure, multiplication, so since Z is closed under multiplication and subtraction, both BC minus AD and BD are integers. Okay. The other part of the definition of rational numbers, you can't have 0 in the denominator. Okay. Can we guarantee that BD is not 0? Yeah, because B isn't 0 and D isn't 0. Neither of those are 0, so they can't. Okay, furthermore, BD is not 0. Okay. Thus, X must be a rational number by definition. Okay. Now, if we go back here, what did we say? Let X be an irrational number. Okay, so we can't have that X is both rational and irrational. That's a contradiction. Okay. So this contradicts the fact that X is actually an irrational number. Okay. So where does that lead us? Well, when we suppose that this was true, it led us to a contradiction. There's no possible way this could have been true because it leads us down to a path that gives us false. This must be wrong. Okay. Therefore, X plus Y is actually an irrational number. That's false, so this must be true. All right. Do you love proof by contradiction? Okay. We'll learn to love it. All right. You have a whole weekend to let it sink in. We'll do a couple more examples to warm up next time, and then we'll do my favorite mathematical induction next time. It's the best.
I haven't seen you struggle over this. Hold on.